So this video is about the binomial distribution, and it's used to predict probabilities associated with a particular situation. And here's the situation. So there's two conditions. First, you have to have a fixed number of independent trials. So a certain situation repeats itself a fixed number of times. That number of times is n, and each of those trials is independent. So the outcome of previous situations does not affect the outcome of the next situation. For example, if you flip a coin 6 times, each time you flip a coin, the outcome is independent of the previous coin flip outcomes. So this is the first condition. The second condition is that each trial, each of those independent n trials, each trial ends in one of two mutually exclusive outcomes. So every single trial can only end in one of two ways, and it cannot end in both of those ways. So those two outcomes are mutually exclusive, right? So we have a reminder of these two terms. One term is mutually exclusive. The other term is independent. So you have a certain trial that's repeated n times, and each of those times the trial ends in one of two mutually exclusive outcomes. For example, you flip a coin 6 times, and each of those times it either lands on heads or tails, not both, that's the mutual exclusivity, and each of those trials is independent. Okay, the next coin flip, its outcome does not depend on the outcomes of the previous coin flips. Okay, so this kind of situation repeats itself many, many times. Okay, you take the elevator 100 times. It either gets stuck or it doesn't. That's a binomial distribution. Okay, you take a particular public transportation route to wherever it is you need to go. You do that 100 times. Each of those times, either you're late or you're not. Independent trials, two mutually exclusive outcomes. So just a reminder of what does this mean, independence and mutual exclusivity. So A and B, two events, are independent if, okay, the probability of A given B is equal to the probability of A. So this is a review of the probability videos. Okay, the probability of A given that B already happened is equal to the probability of A, which means whether B happens or not, the probability of A is the same. If we don't take B into consideration, it's just the probability of A. If we take B into consideration, it's still just the probability of A. The probability of A does not depend on whether B happened or not, and vice versa. The probability of B does not depend on whether A happened or not. If that's the case, then A and B are independent. So what does that mean? Well, if we look at the formula for the probability of A and B, before we would say that this is the probability of B times the probability of A given that B already happened. Because for A and B to occur, you need the probability of B, you need B to happen, and you need A to happen under conditions that B already happened. But if A and B are independent, well then the probability of A given B, that's just the probability of A. And what you end up with is the probability of A and B is just the probability of B times the probability of A. If A and B are independent, The probability of both events occurring is just the probability of one multiplied by the probability of the other. Okay, so that is the first key situation that we're going to remember when talking about independence. Now we'll talk about mutual exclusivity. Okay? Okay, so A and B are mutually exclusive if it means they cannot happen at the same time. Well, what does that mean? It means the probability of A and B is equal to 0. Okay, if they cannot happen together, well then the probability of them happening together is 0. Now what does that mean for the OR operator? Normally the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. That's again the review from the statistics lectures. But if the probability of A and B is 0, well then this last term here cancels out. And what we end up with is that the probability of A or B, it's just the probability of A plus the probability of B. Okay, and that's that second rule that we're going to remember when we're talking about mutual exclusivity. Now, why this is important is because when we're dealing with a binomial distribution, we have n independent trials, which is the first case here. We're talking about independence. In an independent trial, the probability of 2 events happening is the probability of one multiplied by the probability of the other. And each of those trials ends with one of 2 mutually exclusive outcomes. When we're dealing with mutually exclusive outcomes, then the probability of one or the other happening is the probability of one plus the probability of the other. Now, here we're going to deal with an example. Let's say there's a game. Okay? The probability of winning is 0.1. And there's no ties. You either win or you lose. Okay? Which means the probability of losing is everything else. 1 minus 0.1, which is 0.9. So each time you play, there's a 0.1 probability that you win and a 0.9 probability that you lose. So we're going to look at the situation more closely to study the binomial distribution.